Okay, moving on to our next example here. In this example, we have a car traveling along at 20 meters a second, slams on the brakes, and stops in a distance of 50 meters. It says to assume that the deceleration is constant, so we're assuming constant acceleration here. That's good because our force equals ma assumes a constant net force and a constant acceleration. Our kinematics also assume a constant acceleration there. It says the coefficients of friction between the passenger and the seat are static coefficient of friction equals 0.5 and kinetic coefficient of friction is 0.3. Now this should kind of make sense. Generally speaking, our static coefficient of friction is larger than the kinetic coefficient of friction. You've felt this before when you tried moving something that was stationary on the ground and you push and it's really hard, but as soon as you get it pushing, then it starts sliding really easy. It's a lot easier to keep it moving than it is to start it moving. And it's tempting to say, well, that's because of inertia, right? Well, in some way, but it also depends on this static coefficient of friction. When the object is settled, those two surfaces tend to interlock and interact more than when it's sliding. And so sliding coefficient of friction will always be less than the static coefficient of friction. All right. Now the question here is, will a 70 kilogram passenger slide off the seat if they're not wearing a seatbelt? Okay, well, let's think about this. The first question we have to ask ourselves is, why are they asking this question? Why would a person slide off? So the car is moving forward at a speed of 20 meters per second. It stops, so it comes down to a velocity of 0 in a distance of 50 meters. Why would a passenger slide off the seat? Well, because the car is stopping, the person in the car wants to follow Newton's first law, which is that they're going to continue moving. The person in the car was moving. The car starts stopping. Everything connected to the car stops moving, but anything not connected is going to try to keep doing whatever it was doing before, which is moving along at 20 meters a second. So the person's going to try to slide along. Now, the question here is, why wouldn't they slide along? Well, because they're sitting on the seat. And right here, the contact between the person's bum and their seat is going to apply an amount of friction. The person wants to move forward, but the friction is going to apply a backwards force. Now, the question is, how much backwards force does it need to apply? Well, we want the person to accelerate at the same rate as the car. What is the acceleration of the car? Well, we can get that from kinematics, right? We can say we've got an initial position of 0, a final position of 50. We've got an initial velocity of 20, a final velocity of 0, and we can then calculate the acceleration. Which equation do we want to use? Hopefully you're thinking about this one. V squared equals V naught squared plus 2ax minus x initial. We go ahead and put these numbers into that, and you should get an answer of -4 meters per second squared. Now, you'll notice it is negative because I defined, notice that my final position was a positive 50 moving to the right. My velocity moving to the right was positive. So I defined the right as being positive and the left as being negative. So the acceleration has to be negative to oppose that motion, right? So this is the acceleration that the car has. Now, in order for me not to slide on the seat, my acceleration must be the same, or the person sitting in the seat must have the same acceleration. So let's look at the person. What are the forces acting on the person? Well, we've got the force of gravity pulling down on the person. We've got the normal force of the seat pushing up on the person. And then we've got hopefully a little bit of friction pushing back. Now, there are no other forces. There's no force pushing them forward. Remember, they're going forward because they were going forward, and they're going to continue going forward unless something makes them stop. Hopefully, the friction is going to do that. Now, If I accelerate at the same rate as the car, I need this acceleration. What's going to cause that acceleration? Well, it needs to be the friction. The friction is the only horizontal force. These two guys, they're equal. They balance. I'm not going up and down. I'm just either going forward or I'm slowing down at the same rate as a car. So what we want to do is look at the horizontal force, and we want to say, well, how much friction do we need? Well, sum of the forces equals ma. That means I need friction to be equal to my mass times the acceleration being provided. How much friction do I need? I need 280 newtons. That's the force that is necessary for me to be able to accelerate at the same rate as the car. Okay? So if I go at the same rate as the car, I'm not sliding. So now the question is, can friction provide that force? Can friction cause me to slow down with that amount of force? If friction can apply that force, then it will, and I won't slide. If friction cannot apply that force, then I will slide forward. And not only will I slide forward, but the forces will be unbalanced and I will accelerate forward. Okay, at least from the perspective of the car. All right, now, here's the key. Can the friction apply negative 280 newtons of force? Well, we're going to have to go into our definition of friction. We know that friction is equal to the coefficient of friction times the normal force. If it's static, then this is the maximum amount of friction that can be supplied. If it's not static, if it's kinetic, then that is equal to the amount of friction. Now, which friction do I want? Do I want the static friction, coefficient of friction, or do I want the kinetic? Well, we're hoping that I don't slide. That's the question. If I'm sliding already, then we already answered the question. That defeats the purpose. So I want the static coefficient of friction here. How much friction can that provide so that I'm not sliding? Well, let's see. Friction equals the coefficient, 0.5 for the static, times the normal force. Now, the last time, in the last problem, normal force took a little bit more work to figure out because it was on a ramp. This time, it's pretty straightforward because the only vertical forces are the normal force of the seat and the force of gravity, right? And so in this situation, we can say that those two are equal. We know that the force of gravity is equal to the mass times the acceleration. And so when I put those two together, then I get a value of 686 newtons. Now, that's not the frictional force, that is the normal force. Okay, so I'm going to go ahead and put that in for my normal force. All right, and when I multiply those, then I get a value of 343. So, the question here is, I need 280 newtons of force in order to not slide forward, in order for me to accelerate at the same rate of the car. The car seat is able to provide a maximum, because this is static, a maximum of 343 newtons. Therefore, can the seat provide enough friction? Absolutely. In this scenario, yes, the car is going to be able to stop me. I'm not going to go flying out of the car. The coefficient of friction between the seat and me is enough that the passenger is not going to go flying out of the car. Okay? Now, how much friction is the seat going to provide? Well, it's not going to provide 343, because if the friction was providing 343, that would be more than is necessary, and the person would actually accelerate backwards. That doesn't make sense. So how much friction is the seat providing? Exactly enough as what it needs. So the static friction here will be 280 newtons, so that I accelerate at the same rate as the car. but it means that I could stop a little bit faster, stop in a slightly shorter distance, and still that friction would be enough to keep me from flying. Now, please remember that we are greatly simplifying this. We're not looking at any vertical forces like the car tipping forward or, somebody rear-ending us, which would then give a force of the seat on it, right? There's a lot of things that we're not considering here, but in this situation, it would mean that we would be safe, that the seatbelt is not absolutely necessary. Okay, hopefully that makes sense, but I'm happy to answer questions if you have them. Let's move on, and we'll look at one more question.